Welcome everyone to IRIS Biotech's 13th online workshop. True to our slogan, Empowering Peptide Innovation, we're keen on knowledge exchange and getting in contact with scientists all over the world. Therefore, we started this workshop series 3 years ago. Today, our focus is on trifluoromethyl and especially trifluoromethyl thio groups in amino acids and peptides. Our guest speaker, Professor Thierry Brigaud from CY Cergy Paris University, will present interesting results of his long research with these fluorine-containing motifs. My name is Raimund Meyer. I'm working as a COO at IRIS Biotech, and today I will guide you through this workshop. As always, I would like to begin with some technical information. To ensure good data transfer of the presentations, all participants are automatically muted and the video cameras are switched off. This live event is recorded, thus if you enter late or miss anything, please check on the bottom left side of your Teams screen if you are watching the recording or if you are live, which is shown by the red broadcasting symbol. You have the possibility to pause the video, rewind, or jump back to the live session. In addition, the recording of the workshop will be uploaded on our homepage afterwards. Questions can be submitted by using the Q&A chat of Microsoft Teams. You can enter your name or submit your questions anonymously. Initially, your questions are just visible for the organizers and will then be published to the audience, so don't worry if your submitted questions do not appear on the chat screen immediately. If you have any technical queries, you can also submit them in this Q&A chat. Our technical assistant will then connect with you and try to solve the problem. I would now like to give you an overview on today's agenda. We'll start with a short company and topic introduction by our Chief Marketing and Sales Officer, Karin Rustler. And afterwards, our external speaker, Professor Thierry Brigaud, will present to you fascinating examples of his work with fluorinated peptides. As mentioned, questions will be collected throughout all talks in the Q&A chat, but of course, you can also get in contact via email or phone call after the workshop. Let's now continue with a short introduction to our company by our CMSO, Karin Rustler. Karin obtained her doctoral degree in organic chemistry at the University of Regensburg. Beginning of 2020, she joined IRIS Biotech as a project manager, and in the meantime, she is now our Chief Marketing and Sales Officer. Karin, thank you for your time. Please go ahead with your presentation.
Thank you, Raimund, for the kind introduction, and also welcome from my side to today's workshop. As Raimund mentioned, I will start with a brief company introduction for those of you who do not yet know IRIS Biotech. And for those of you who already know IRIS, don't worry, I will keep it short. So for this slide, I will just focus on a few aspects. The company IRIS Biotech has been founded in 2001. Our portfolio comprises more than 6,000 different products. Of course, we cannot produce all of them in our own synthesis laboratory in Willstedt, but we are working together with different manufacturing partners around the globe to realize demands from milligram up to kilogram quantities for research purposes up to GMP quality. To give you not only facts and figures, I want to share a picture of the beautiful landscape we are surrounded by. So I can highly recommend visiting the beautiful so-called Fichtelgebirge if you're going on holiday in Germany. On this slide, you see a picture of our company building, where we are operating from and where your orders are being processed. As mentioned briefly already in the beginning, on the one hand, our mission is to support our customers in their ongoing projects from research scale to commercial production. And in this regard, we are mainly active in the field of peptide synthesis and modification by providing amino acids, resins, reagents, and solvents, but also in related fields such as linker technologies and products for drug delivery. But for us, our slogan, Empowering Peptide Innovation, does not only mean to provide innovative products, but also to act as some sort of scientific advisor by providing and exchanging knowledge. In this regard, we built up our own knowledge base which includes topic-specific brochures and flyers, which can be downloaded from our website. In terms of today's topic, I would like to highlight our flyer about fluorinated derivatives, as well as our previous newsletter about SCF3 derivatives, which is available on our website. Besides, we are publishing a bi-weekly newsletter, and if you are not yet registered, please refer to the link shown on the top right side. And yeah, with this, I would already like to thank you for your kind attention. As promised, I kept it short, and now let's pass on to the real highlight, our guest speaker.
Yeah, thank you, Karin, for giving this introduction. Now let's really go on with our highlights, switch to our speaker, Professor Thierry Brigaud. Thierry received his PhD from the University Claude Bernard at Lyon in 1990. He was then appointed as full professor at the CY Cergy Paris University in 2002. Additionally, he was the director of the Laboratory of Chemical Biology for 7 years. He's currently deputy director of the BioCIS and director of the chemical biology team of the BioCIS. His interests include chiral fluorinated compounds such as amino acids, amino alcohols, or amines, and the synthesis then of fluorinated peptides or pseudopeptides and their biological applications such as inhibition of amyloid peptide aggregation, nociception, antimicrobial peptides, protease inhibition, and many more. Thierry, it's a great honor to host you as our guest speaker. The stage is yours. We're looking forward to hearing about your research. And for the audience, please post your questions by using the Q&A chat.
Okay, thank you very much, Raymond. So indeed, today I will present what we are doing in Cergy, in the Biosis lab since several years around fluorinated amino acids and their use as tools for the tuning of peptide hydrophobicity, conformation, and proteolytic stability. So our lab, yes, is located in Cergy-Pontoise, which is close to Paris, and several teams, 4 other teams of Biosis lab are in Paris-Saclay University, and we are also a joint unit with CNRS. So. Why fluorine? So fluorine in medicinal chemistry is a well-known element and a very popular element because it provides specific properties in pharmaceutical compounds. And as you can see, more or less each year, there are in between 25 to 50% of new approved small molecule drug containing at least 1 atom of fluorine. In peptide as therapeutics, peptides present a lot of advantages of strength and positive parameters such as their high selectivity and potency, good tolerability and safety, a predictable metabolism because they are constituted amino acids, and they can be synthesized by standard synthetic protocols which can be automated. The weakness for therapeutic use of peptide is that they are prone to hydrolysis and to oxidation. They present generally a low membrane permeability, a short half-life and fast elimination, and generally they are not orally available. Anyway, there are an increasing approval of peptides since the 60s. So as you can see on this chart, the use of peptides as drugs is increasing. And even if it represents a small part of all the global pharmaceutical market, it's at the interface in between biologics, which are increasing, and small drug molecules. So they are supposed to increase. What would be the interest of incorporating fluorine in peptides, fluorinated amino acids in peptides? So first of all, there is no natural fluorinated amino acids. So we have to synthesize these compounds. So what can be expected? First of all, a modification of the neighboring functional group polarity and pKa. For example, here on this kind of amino acid, you will increase the NH donating H-bond donating effect of this amide function here because the fluorinated group is electron withdrawing. Here you also provide a steric hindrance, which should protect also the amide bond from hydrolysis. So an increase of hydrolytic and proteolytic stability can be expected. Of course, as this nitrogen here is less basic, it will reinforce this amide bond towards hydrolysis here, because for hydrolysis, at what time or another, you should protonate this nitrogen. The hydrophobicity of fluorinated group is well known, so can be expected a better affinity for membranes, and which could favor interaction with hydrophobic pockets of receptors. Fluorine induce also fluorinated group induce conformational restriction. So I will show you some example with the cyclic amino acids or pseudo amino acids surrogates. And very original is the use of fluorine as an NMR probe, because you know that fluorine 19 is as sensitive as proton in NMR. So the challenge, of course, is the synthesis of these amino acids. And they should be synthesized in enantiopure form, because you know that it's mandatory to have enantiopure amino acids if you want to incorporate them in peptides. What is important also is the development of scalable methodologies, because if you want to use fluorinated amino acids and to incorporate them in peptide, you should be able to produce gram and gram amount of amino acids. Some challenge also have to be overcome, such as the peptide coupling, because you can imagine that here the peptide coupling on this nitrogen, which is deactivated by the electron withdrawing CF3 group, will be quite difficult, and because this nitrogen is not very nucleophilic. Anyway, we developed several strategies for the synthesis of these amino acids, and as you can see, yes, on this scheme, we developed in Sergi chiral alpha disubstituted CF3 containing amino acid, just like trifluoromethylalanine. So I will show you some examples, and as you will see, we are able to synthesize both enantiomer in enantiomeric pure form. Functionalize the side chain amino acids, beta amino acids, CF2H, recently we developed a CF2H amino acid. So these ones are quite interesting and promising because this proton is an H bond donor, so it's interesting. SCF3 amino acid, which provides a lot of hydrophobicity, such as trifluoromethylcysteine, trifluoromethionine. Recently, also, we developed the electrophilic SCF3 incorporation methyl group, SCF3 group on aromatic compounds, such as tyrosine, tryptophan. And also, we developed cyclic amino acids, such as aziridinic, azetidinic amino acid, proline amino acid with a CF3 group at different place in alpha position, in the 5 position, controlling the chirality of these centers. We did also pipecolic amino acids, and very interesting pseudo-peptidic pseudo-amino acid units, which are the pseudoproline. So this oxazolidine looks like proline here, and we have an oxygen or a sulfur atom in place of this CH2 group. And these pseudoproline, I will show you, are very interesting for the constraint of conformation of peptides. The strategy we developed for the synthesis of these amino acids so it implied the following strategies. This deconnection is virtually unknown, so it's difficult to synthesize trifluoromethyl amino acid, alpha trifluoromethyl amino acid from an amino acid just by trifluoromethylation. The technology and the strategy we developed were mainly involving the Straker type reaction. So starting from fluorinated ketones or aldehyde, which are industrially common compound, and we synthesize with an amino alcohol, such as phenylglycinol. Condensation reaction provides this oxazolidine. And by a Straker type reaction, under Lewis acid activation of the deoxazolidine, we obtain this amino nitride. And this amino nitride can be hydrolyzed here and to give the carboxylic acid. Removal of the phenylglycinol side chain will provide the amino acid in enantiopure form if here you separate both diastereomers. So that's the base of our strategy. Another strategy is starting from trifluoropyruvate, which is a commercially viable compound. And here, as you can see, you have the fluorinated group. You have already the carboxylic group, so you don't have to use Straker reaction. And if you build an oxazolidine of this trifluoropyruvate, you have here the nitrogen of the amino acid. So you just have to activate this oxazolidine and here to do a Lewis acid mediated reaction in order, for example, to incorporate an alkyl group here. And after separation of this diastereomer and removal of the side chain, hydrolysis of the ester, you obtain the amino acid. So I skip this one. It's just to show, depending on the fluorinated ketone or fluorinated aldehyde you start from, you can obtain several differently substituted oxazolidine. So this kind of oxazolidine or this kind of oxazolidine, if you start from acetoacetate, and if you want to introduce the longer chain here, we have all the technology and the strategy, yes, to build any kind of oxazolidine with any kind of bond length here. And from this oxazolidine, mainly by the Straker type strategy, we obtain amino acids. So some example, I don't want to feed you too much with organic chemistry, because we have to see what can we expect of this peptide, the incorporation of this peptide, of this amino acid in peptide. Just give you quickly some examples. So for trifluoromethylalanine, we can do it on large scale. So from this oxazolidine, by Straker type reaction, we obtain these two aminonitrile. As you can see, it's easy to do the separation of these two diisomers. And then in a one-step procedure, at the same step, we hydrolyze the nitrile and we remove the phenylglycinol side chain in order to obtain the trifluoromethylalanine. So we obtain the R1 or the S1. Very recently, we also synthesize difluoroalanine according to the same procedure, starting from this oxazolidine. For functionalized side chain, we use quite similar strategy here. For example, for the synthesis of the trifluoromethylserine, starting from the oxazolidine, reduction of this ester to give the alcohol, the methyl alcohol side chain of the serine. Straker type reaction, we have the aminonitrile, and then in a one-step procedure, we remove the side chain and we hydrolyze the acid and we obtain the trifluoromethylserine. It's possible also to do the cyclization here in order to get trifluoromethyl aziridine amino acids. Another example here with the homologue here, it's easy to build by the same strategy aspartic acid according to the same kind of procedure involving TMS-CN Straker type reaction. For cyclic one, we developed several reactions involving cyclization in this kind of bicyclic compound, this oxazolidine, and then Straker type reaction on the cyclic oxazolidine to get, in a few steps, after hydrolysis of the nitrile, removal of the side chain, these amino acids, for example, pipecolic acid, alpha-proline, and so on. So, for example, it's possible by this method to obtain this kind of bicyclic compound and to provide acetidine, higher homologues such as proline, so SCFM proline, RTFM proline, or pipecolic acids, S or R, are obtained by the same methodology. It was interesting for us also to develop method to incorporate a CF3 group in this position of proline. So we provide a multi-step strategy involving the addition of trimethylsilane on pyroglutamic derivatives. And we obtain, like that, this cis 5-CF3 proline which doesn't epimerize, so it's configurationally stable, in good yield, and in enantiopure purity. So we were also interested in obtaining this other diastomer, also in diastomerically pure form. So it has been done by reduction. So as you can see, even if this compound is very interesting, it requires several steps to provide these amino acids. So that's why we developed this pseudoproline strategy, which is in fact very interesting because you obtained here this pseudoproline in a one-step procedure. So the strategy is the following: starting from a fluorinated hemiacetal of trifluoroacetaldehyde or a fluorinated ketone with a serine derivative. So we use the amino alcohol part of the serine to build pseudoproline. And compared to their non-fluorinated analogs, these pseudoproline are completely stable. That means there is no epimerization of this center here, even in a slight acidic acid, which is not the case, of course, of non-fluorinated one. This is due, in fact, to the electron withdrawing effect of the CF3 group, which stabilizes the configuration here. So it can be done on ketones. Starting from cysteine, it's possible to obtain these cysteine-like pseudoproline. From the difluoroacetaldehyde derivative, it's possible to obtain also stable difluoromethyl containing pseudoproline. And as for the CF3 one, both diastemer are easily separated and are completely stable. Another family of amino acids that we developed are the SCF3 containing amino acids, because it is known that the SCF3 group in medicinal chemistry is providing a lot of hydrophobicity. And it has not been developed so much in peptide chemistry yet, because it's necessary to synthesize the SCF3 containing amino acids. So we revisited the chemistry of Bernard Langlois and Thierry by SCF3 radical incorporation on the CF3 radical addition of on the disulfur here by this reagent, which gives a trifluorocysteine or trifluoromethionine protected by a Bock group here. It's also possible to use a Togni reagent and to provide a FMOC protected SCF3 containing amino acids, which is in fact the trifluoromethionine. So this trifluoromethionine is synthesized in a few steps and in good yield by this methodology. So the Bock protected one can be incorporated in peptides by solution phase strategies, and this one can be incorporated in peptide by SPPS without any problem. Recently, we developed the synthesis of SCF3 containing amine and amino acids. So on this slide, you have the electrophilic SCF3 incorporation on tryptamine analog, on serotonin analog, on melatonin, and so on. So it has been done in collaboration with my colleague Gerney Iskra from Ljubljana. And this chemistry, of course, is possible and is efficient on tyrosine and on dopamine, tyramine, and so on. So here, as you can see, we can synthesize the SCF3 tyrosine in one step from the FMOC tyrosine. The reaction is a ratio selective. SCF3 is only in that position. So we did also several analogs. And also this chemistry, I don't have it on this skin, is also working, yes, on tryptophan. It's here, and the reaction on the tryptophan. So tryptophan, tyrosine, DOPA, and so on. Okay, so now that we have these amino acids, what about their incorporation in peptide? So as you know, generally for incorporation of amino acid in peptide, we have to use protected amino acids. So first we developed the solution phase incorporation of these amino acids. And as according to our methodology, in fact, very often we obtain completely unprotected amino acids because the last step is an acidic treatment, and we have the amino acid, for example, trifluorinated alanine, without any protecting group. And we, in fact, imagine that it could be possible to do peptide bound on this carboxylic part of the amino acid without protecting this NH2 group. And indeed, it's working if we proceed by this way. For example, we add first the non-fluorinated amino acid, then the coupling reagent, and then we add this fluorinated amino acid. And here we can obtain the peptide coupling, this carboxylic position, without protecting this one, and the yield are quite good. Of course, the problem will be difficult on this for the coupling on this amino group, which is strongly deactivated and also hindered here. And we tested a lot of coupling reagents, and what is working, in fact, and working quite nicely, is the coupling of FMOC amino acid chloride. So we generally prepare this chloride by starting from the FMOC amino acid by treatment with SO2Cl2, and we obtained so this amino acid chloride, and the other possibility is to use the isobutyl chloroformiate here in order to provide as an intermediate this mixed anhydride, which is electrophilic enough to give the peptide coupling, the coupling on this position. Okay. So now for some application that we developed in the lab. For example, we explored the biophysical properties of peptide incorporating this fluorinated amino acid. For example, for the hydrophobicity, proteolytic stability, conformational constraint, use as fluorine 19 probes. And I will show you some application around beta amyloid aggregation inhibition, enzyme inhibition, antimicrobial peptides, collagen mimetic peptides, poly-AIB foldamers. So these are the most recent research we undertake in Cergy, incorporating fluorinated amino acids in foldamers. So I will not enter in detail, but there is a very interesting method to probe the hydrophobicity of peptide by reverse phase HPLC. And these methodologies allow the determination of hydrophobicity index. So this hydrophobicity index, in fact, is a result of the the capacity factor, and there is a formula here depending on the capacity factor of the chromatogram we obtained. So what we did, in fact, we synthesized this tripeptide, always the same tripeptide, changing only the amino acid here at the middle. So the hydrophobicity, the difference of hydrophobicity index of this peptide will depend only of the amino acid, which is at the middle. So, for example, with alanine, the hydrophobicity index of the peptide, so bleu, is 4.1. If we add another methyl group, for example, we increase the hydrophobicity. So with the 2-methyl here, aminoisobutyric acid, we double here, the hydrophobicity index is 8.9, and so on. If we incorporate SCF3 group, so methionine is more hydrophobic. Then we probe tyrosine, isoleucine. So isoleucine is known to be the most hydrophobic amino acid, aliphatic amino acid, and the hydrophobicity index of this tripeptide, incorporating here isoleucine, is 13.8. Tryptophan is very hydrophobic also, as you know, and this is here is hydrophobicity index. So what happened with the fluorinated one? And as you can see, when you incorporate fluorine, you will increase strongly the hydrophobicity. And on this scale, as you can see, just one CF2H is providing as much hydrophobicity as isoleucine. And the major advantage is that this one is less steric hindered than isoleucine. So if you want to provide for specific pocket hydrophobicity without steric hindrance, this group will be very interesting. Also, this one, trifluoromethionine, is very interesting because it's less hindered than other amino acids, and it's very hydrophobic. With Gilles Guichard and Guillaume Campin, our colleague, who developed recently the synthesis of hexafluoroleucine, we measured the hydrophobicity index, and as you can see, it's almost the same. Trifluoromethionine and this hexafluoroisoleucine have quite similar hydrophobicity. And the winner of the winner is SCF3 tryptophan, which is today the most hydrophobic compound, amino acid that we know. So the idea sometimes is to provide hydrophobicity, but not to provide whole hydrophobicity of the whole peptide, because the interest is to provide local hydrophobicity. For example, if you want to target a specific hydrophobic pocket of a protein, for example, or an enzyme, it could be interesting to put just a fluorinated amino acid at this place in order to have a good recognition. Some applications connected to hydrophobicity. So you know that amyloid beta, the aggregation of amyloid beta is provided by starting from a hydrophobic core side chain, which promotes amyloid aggregation on the KLEFF part here to give beta-hairpin and then fibrates. So our idea was to check if a small beta sheet breaker, small peptide hydrophobic could disrupt this aggregation. So we synthesize this tripeptide here, and this tripeptide was submitted to the thioflavine T fluorescence test to see if we could inhibit somehow the aggregation of amyloid beta. And indeed, we decrease here the plateau. And the fluorinated amino peptide here, this one is a little more efficient than the non-fluorinated one. So we have the effect of hydrophobicity here. So yes, it's a proof of concept. Another aspect, we know that MIF1, this peptide, so without the CF3 here, is an analgesic peptide. And so we synthesize this CF3 analog of this MIF1 peptide. And here, as you can see, we have a better analgesic effect with the fluorinated one. And in collaboration with Meredith Exedo, we showed that this effect should be due to the increase of hydrophobicity, providing an increased passive diffusion transport. So it has been demonstrated by the PAMPA system, parallel artificial membrane permeability assay, and we showed that the fluorinated containing peptide here has an increased hydrophobicity and also an increased passive diffusion transport through the membrane. Another example, maybe due also to hydrophobicity, I explained to you, yes, that we could easily synthesize SCF3 tyrosine and SCF3 tryptophan. So there is a beautiful peptide, which is endomorphin 1, which is an agonist of a new opioid receptor, having a tryptophan here and a tyrosine here. So we could synthesize by SPPS using Liberty Blue synthesizer, SCF3 containing, tyrosine containing endomorphin 1, and SCF3 containing tryptophan. And these endomorphin are currently in biological evaluation. Conformational constraint now. So the fluorinated group increase stability, of course, towards the ring opening of oxazolidine. So that means that we can use these oxazolidine as really a stable compound. So what's about the proportion of cis and trans amine bond on this oxazolidine? So here you have the ratio of cis and trans amide bond here with proline. With the CF3 in this position, we increase the cis content. With the CF3 pseudoproline, we increase also the cis proline. And with the CF2H, we increase here, and more importantly, the cis content. And the best result we obtained is this diastereomer here. In chloroform, we have almost 80% of cis conformation of this amide bond. So it was quite intriguing. And also, as we check the NMR, we saw that there was a big, the two fluorine were highly diastereotopic. And it was connected, in fact, to an H bond here, stabilizing the cis conformer here through an H bond here. So it's a very interesting aspect. and it reveals the specificity of this CF2H group, which is in fact hydrophobic. You remember, almost as hydrophobic as methionine, and of isoleucine, and also it's nitrogen donating group, and a hydrogen bond donating group. Okay, some other aspect connected to conformational constraint here. We discovered that we could control the conformation of these oxazolidine depending on the configuration here of this SCF3 group. And like that, we could synthesize collagen model triplet and providing and showing these alternance of S-pseudoproline, R-pseudoproline, glycine, which is a mimic of proline, hydroxyproline, glycine of the collagen tripletics. And we incorporated this one, so this triplet here, in a collagen mimic system, and indeed we could synthesize a tripletics. And it has been shown that in fact, even if the CF3 group are in this position, they don't disturb the structure. Another example, fluorine NMR here, as you can see here, if you put fluorinated amino acids, for example, on a peptide here, by NMR, you can monitor the hydrolysis of these, or the stability, of course, of this peptide. For example, here, this peptide, we showed that only 40% is cleaved by pepsin after 24 hours, when the non-fluorinated analog is cleaved in 1 hour. It's very fast. Also, it's possible to we could demonstrate that the cleavage site is not the classical cleavage site with the pepsin, but the peptide is cleaved here. So we showed that the incorporation of this trifluoromethyl amino acid here in this position protects this peptide bond towards hydrolysis. I think I will not have to show this one. I will finish because I see that time is almost over. I will just finish by recent results connected to incorporation of fluorinated amino acid in peptide in Foldamer's conformation control. So you know that poly-AIB peptide here are Foldamers, so it's the chemistry of Jonathan Claydon, and it provides a stable 310 helix. So of course, if you have just AIB here, if you have just achiral monomers, you will have two screw ends and you will have two 310 helix, which are in equilibrium. The M left-handed helix and the right-handed helix. Jonathan Claydon showed that if he used a chiral controller here, for example, this alpha-methyl valine here, he can control here the chirality of the helix. And it gives, for example, with this one, when you have the S alpha-methyl valine here, the right-handed helix. So we wanted to see what will happen if we put a CF3 in place of this isopropyl, because it's known that sterically isopropyl and CF3 are almost the same, give almost the same hindrance. So we did this peptide, and our big surprise was that in this case we had a left-handed 310 helix, so an opposite sense. So it's very clear here, as you can see, on the CD. And if we use you incorporate the amino acid here with the S configuration here, so the other enantiomer, we have the same right-handed helix than with Jonathan had with the alpha-methyl band. So we probably showed that we have the hydrogen bond pattern of 310 helix. And what's the difference in between the two? In fact, here with isopropyl, you have a steric adjustment providing the P right-handed helix. And if we have a CF3 group, which is electron withdrawing, there is a polar effect. That's our interpretation. And there is an alignment of the CF3 carbon CF3 group with the carbonyl, which gives the left-handed helix. And the last slide here is the advantage also of fluorine 19, that by fluorine NMR, it's possible also to measure the helicity excess of one helix compared to the other. Indeed, at fast exchange regime, that means at room temperature, the two helix are in equilibrium. But if you decrease the temperature here, you will have two different helix, and the two helix here will be frozen. And like that, by integration, you have at a slow regime the proportion of the M and P helix. So it has been measured for both S or R trifluoromethyl incorporated amino acids. And by this method, we could evaluate that the helical excess is 70%. Okay, so I thank rapidly all the colleagues. There are so many, my colleagues from the group, the PhD student, postdoc, and collaborator from University, Claudio Dalbit for the NMR and so on. Okay, and I will finish by an announcement. My colleagues, Grégory Chaud, Maud Laregola, Pierre Milbeo, and Chiara Donato are organizing in October non-canonical amino acids in Paris. It's a two-day symposium, tools for biological and biophysical investigation, with these wonderful invited speakers. And I think that this symposium is completely connected to what we are speaking today about around non-canonical amino acids. And by the way, as you can see here, you will have Beate Koch, who is, yes, the major player in fluorinated amino acid, and that most of you, I suppose, know. Okay, so thank you for your attention.
Well, thank you so much, Thierry, for sharing your results with us. As you can imagine, we collected quite some questions during your talk. So the first one is, can you comment on how the hydrophobicity can be fine-tuned, going, say, from monofluoro to difluoro to trifluoromethyl? Does that make sense? We saw in one example that it also may have effects due to H bonding, but does it make sense to do a fine-tuning from mono, difluoro, trifluoromethyl?
So we didn't test the monofluoro, but I think that monofluoro should be a little bit polar, maybe. Maybe monofluoroalanine will be more polar than difluoro. But difluoro is, yes, indeed, is hydrophobic, and trifluoromethyl is much more hydrophobic. Maybe I can see on the on this scheme here. Okay, so it's here, as you can see, difluoromethyl. So this one, it was a surprise because, to my opinion, I imagined that difluoromethyl could be more polar and less hydrophobic than, for example, methionine or isoleucine. But in fact, not. As you can see, it's as hydrophobic as isoleucine. And
Okay, thank you.
And it's an H bond donating group. Are not as strong as an H of amide. So that means that in a peptide, for the structuration and the conformation control of and the folding of peptides, the NH donating effect of NH of amide bond with a carbonyl of peptide bond is much more important than the side chain. But the side chain is exposed to the protein and to the partners. So as a side chain, it's interesting.
So one more question about the hydrophobicity. So hydrophobic interaction has been utilized in the last years, especially with the GLP-1 analogs, to make them bind to albumin via a long aliphatic chain. Can the introduction of CF3 or SCF3 groups also, say, mediate a binding to albumin, or is this not enough?
Yes, I think it should be tested. Because
so you have no experimental data on that?
Yes, because and even with shorter chain. So maybe it could be interesting, yes, to compare a very long aliphatic chain here compared to a shorter SCF3-1.
Yeah.
Okay, but
nice idea.
Yes, the interaction, yes, with albumin is a relevant model of interaction with a protein.
Yeah, right. So also to the hydrophobicity, seems to be somebody who's doing peptide synthesis. Often technical problems arise when peptides are becoming too hydrophobic.
Yeah.
So when does it really make sense to make tryptophan, which is so hydrophobic, even more hydrophobic by adding SCF3? So you showed the one example on a very short, very small molecule, but does it really often make sense to make the tryptophan even more hydrophobic?
Yes, to my opinion, it depends what you want to do. Of course, to my opinion, it's stupid to do a whole hydrophobic peptide because, of course, it will precipitate. We will have a lot of problem. Hydrophobicity, too much hydrophobic peptides are a problem. But here, what we are doing is just to increase hydrophobicity at a specific point here. And with endomorphine, globally, we measure the hydrophobicity of the whole endomorphine and the hydrophobicity of the SCF3 tyrosine or SCF3 tryptophan endomorphine, and there is a little hydrophobicity difference, but not that much. So we had no problem, yes, for these to extract them for the synthesis. But what is very important is the local hydrophobicity introduced in that position in between the SCF3 tryptophan and the normal tryptophan. Because here we focus the interaction with the opioid receptors. So to have hydrophobic group in this position or increase hydrophobic specificity in this position is very important for the biological aspect and also for the selectivity towards different opioid receptors. But I agree that doing a whole polytryptophan chain, maybe is not very interesting.
Okay, so then one question to the structure function relation. You showed that you can influence the cis-trans ratio in prolyl bonds, and by adding CF3 or CHF2. And does that only affect the ratio between cis and trans, or does that also affect the speed of the isomerization?
Yes, it's I didn't. There is so here you have the trans cis
Activation energy.
transition state
Yeah.
energy here. So this is interesting. Is that here to go from the trans to the cis, you need 20 kilocalorie, and if you put some fluorinated oil, as you can see, you have 15. So you decrease the energy which is necessary to go from the trans to the cis. So you accelerate the isomerization. So that means that the hinge, because this cis-trans isomerization of proline in peptide is a very, very important process to control the folding of peptide. So here, so that's why we are investigating the incorporation of pseudoproline for rotamase inhibition, for example, the cis-trans isomerase inhibition, because here we should have some transition state mimic, because as the energy is decreased, we should have a better transition.
Closer to the transition state, yeah. Yeah, understand. Okay, so then some more technical questions. The one is, are your fluorinated amino acids easily incorporated into peptides by SPPS? You already answered that a bit later.
Yes.
So typically it's a bit harder to bring them in, or to bring the next amino acid in, right?
Yes, so that's why if you want to incorporate, it depends which amino acid. For example, if the fluorinated group is on the side chain far, there is no problem. For example, SCF3 tryptophan, all these one are methionine, trifluoromethionine are easily incorporated by SPPS classical method. But for the alpha trifluoromethyl one, or the quaternary one, it's quite difficult. So we prefer to synthesize a dipeptide building block in solution. And this FMOC dipeptide building block is incorporated then after in SPPS.
Okay, that's a good trick, say, to bring
all these amino acids are on the catalog and of IRIS, but I would suggest to people, if they want to incorporate an alpha trifluoromethyl amino acid, they should consider first the synthesis of the dipeptide, and they can also ask for the dipeptide. We can do it. The dipeptide, so to think which amino acid they want before, and like that, this dipeptide building block can be incorporated by SPPS, but the alpha trifluoromethylalanin, it's very difficult to incorporate it as it like that in peptide.
So the dipeptide building block really makes sense in that context.
Yes.
And one last question is about the chemical stability of the halogenated amino acids. So do you sometimes see any loss of fluorine, or is it completely stable over time?
These one are completely stable, completely. Even, for example, the trifluoromethyl containing pseudoproline, they are stable in TFA.
Okay.
So that means that we can incorporate them in a peptide, and when by this PPS, and when we remove the peptide from the resin, we keep the pseudoproline.
Okay.
We have one example, difluoroalanine, for example. With difluoroalanine, you should avoid too much basic condition, because here you will eliminate HF. Because this one has an acidic proton in alpha position, and
yes, yeah,
yes. So this one is an exception, and it's the only one. But we incorporate difluoroalanine in the peptide without any problem and without epimerization. So that means that it's stable once in a peptide. But you should avoid strong elimination condition. But for example, removal of a FMOC group is compatible because we synthesized the FMOC difluoromethylalanine and we incorporated in a peptide without any problem. So, but strong basic condition, yes, should be avoided.
Okay, so that's, I think, all the questions we got in.
Yes, thank
Thierry,
you.
Thank you once again.
Question.
It was a pleasure to have you as our guest speaker. So as we don't see any further questions right now in the chat, if you have any questions left, do not hesitate to contact us also afterwards. Send them via email. We will forward them to Thierry. And with this, we would like to close our online workshop for today. As a follow-up, we will provide the recordings. We hope you could collect some helpful ideas and information from this workshop, and you can gain some interesting own experiences with those halogenated variants. As you can imagine, what a surprise. Karin already told you, you can acquire several of the CF3 and SCF3 modified amino acids from today's presentation from Iris Biotech. Just check our web shop or the flyer or our blog entries on the webpage, or if you have questions, just contact us. Thanks again for joining us. Thanks to all our speakers, and also a big thank you to our QA manager, Klaus Helm, for taking care of the technical support. We're looking forward to meeting you again in the next workshop in September, which will be announced on time. And before that, we would be happy to talk to many of you at one of the upcoming peptide conferences, for example, at the EPS in Florence or in autumn in Paris. Until then, enjoy a beautiful summer, stay healthy, and hopefully see you soon. Goodbye.
Bye.
Bye.